In this video, let's talk about a RC oscillator. RC oscillator is a very simple circuitry and very easy to build, and it's very popular to work as a not so accurate frequency oscillator in FPGA microcontroller, for examples. So recently, I built RC oscillators, but I found the oscillation frequency is much higher than the value I expected. So what happened really? So let's draw a RC oscillator here. If we have a C, it's a capacitor to ground, and you have a resistor R like that, and you have an inverter. Inverter has a ground, have a VCC. So this is a very simple circuitry, okay? And we have C and R there. Okay, let's assume in the beginning we have 0 volts here. So 0 volts pass the inverter. The inverter will invert the signal, invert the low to high. So output will be VCC, let's say 5 volts, for example. What happens if you hear 5 volts? This 5 volts will go through this path, charging this capacitor via the R, okay? Then the capacitor, the voltage of the capacitor will slowly goes up. That's a typical capacitor charging curve. And at 1 RC constant, if you know that, it will be charged up to about 63%. You approach to the maximum, but you never reach 100%. Okay. When these values keep going up, when the voltage here passes threshold of this inverter and is high enough to pass this threshold, the output flipped to low. So, and when it's flipped low, then the capacitor will start discharging via the inverter. Okay, so you have a discharging. So then when you discharge low enough, you go up again, so the cycle repeats. Okay, same straightforward enough, and let's put some values to see if the C is 1 microfarad, R is 1 megohm, so just some very easy to calculate value. And the tau, the RC constants, R times C, which is 1 microfarad times 1 megohm, it's 10 to minus 6 farad times 10 to 6 ohm, which is close to 1 second. And because you need 2 cycles to form the one period wave, so that roughly, if you believe this is true, your oscillation frequency will have close to 1/2 seconds, about half hertz. But if you actually build this structure, you will find out the oscillation frequency will be much higher than half hertz. So the tricky part or the magic part is the inverter. So inverter, it's a very simple logic device, but it's not just magically invert the signal. Essentially, inverter is like a comparator. Okay, you have an input signal here, and you have a reference signal. Let's see, we have VCC and ground. Let's say the reference is 5 volts VCC. We have a reference voltage like 2.5 volts. We have a reference voltage in the middle. So if it is higher than 2.5 volts, because this is on the inverting side, so higher than will output low. And if it's lower than 2.5 volts, output will be high. So that sounds reasonable enough. But in reality, the reference signal here, it's not actually 2.5 volts. Because what happens if it hears 2.5 volts, if your input signals happen to be a signal like this, very noisy, but average around 2.5 volts. If you have a signal like that, you have a DC components average 2.5 volts, but with some AC noise on top of that. When you pass these signals, you know that because it just keep going, cause all these small glitches. Right, keep go up and downs because you quickly go through the threshold, go higher or lower, go like here. Clearly, that's not true. That's not real signal. That's why all the inverters have a built-in hysteresis. If you look at the symbols with the inverter, normally they have draw the inverter like this. like with a hysteresis. What really happens here, if you have an input, and when you compare these values, you actually compare these two values. You have a 2.5 volts, for example, as your median value, middle value, and you have a 2.7 volts, for example, and a 2.3 volts. Okay, to output the logic high signals, in this case, in the inverter case, you have to below than 2.3 volts. To output a logic low signals, you have to above 2.7 volts. Okay, if your input voltage happen falling in between the 2.3 to 2.7 volts, it just basically undefined. Okay, so in this case, you will not have this glitchy problem, although your glitch is not at large. If the glitch is larger than that's the hysteresis, you trigger a signal. If it's below the hysteresis, you will not trigger a output signals. Okay, with this knowledge, now we can go back to here and just look this diagram again, say what really happened in this circuitry here. Okay, and same, if we assume 0 volts start, let's draw it here. We have 2.5 volts as the middle value, and the 2.7 volts, and the higher minimum, high maximum, and the 2.3 volts and the minimum. So what happened here? If you have 0 volts, you start from a very low 0 volts. It will be high here, then you start charging up the capacitor. The value will go from 0 volts, for you can see from here. 0 volts going high will start really going high. You pass 2.3 volts, pass 2.5 volts. Whenever you only trigger the output states whenever you pass 2.7 volts. Okay, so when this is go about 2.7 volt, when the charging values all the way go about 2.7 volts, let me clean up here. When this go to charge up 2.7 volts, then this state flip from 5 volts to 0 volts. Then you can start discharging. Okay, you slowly discharging until you reach 2.3 volts. Okay, then your state flip again. So state flip from low to high again, low to high. That means, so you're charging again, so you're discharging again. So then the cycle begins. So now the difference you can tell, in the previous situation when we first try to understand this, we are assuming we oscillate start from 0 volts all the way to whatever the threshold, the maximum threshold, 2.5 volts, like oscillating like that. It's actually not true. The oscillation happens between these two threshold values. Basically, the oscillation, the amplitude of oscillations decided by the hysteresis values. The hysteresis values, it's depends the components. For example, the inverter inside my FPGA is probably very low, like 50 millivolts. So if your hysteresis is very low, that means your oscillation happens really fast. You oscillating between this upper threshold and lower threshold, upper threshold, lower threshold. Okay, so your oscillation will be much faster than you expected. Actually, I mean, you can basically you can theoretically you can calculate the oscillation values. For example, you can assume, because this value, the range is very small, you can assume it's a linear curve, it's a straight line, and you can, based on RC constant, you can calculate that. So I'm not going to do that. The easier way probably just build the circuitry, do some measurements. I think the takeaway here is the principles stay the same. It's just like most videos or textbook explained, just charging, discharging. But what happens is really the oscillation happens between these two threshold values. So it's decided by the hysteresis. Hopefully this video can help you to understand the RC oscillator more and better. Thank you.